Hi, here we are discussing about a project efficient pseudo random number generator PRNG designs on FPGA. So this research presents the designs and analysis of a pseudo random number generator utilizing 8-bit, 16-bit and 32-bit polynomial to evaluate the durations before the repetitions of random sequence. So this study addresses key challenges in PRNG, the invertible repetitions of output sequence which compromise the quality of randomness and security in your cryptography applications. To mitigate these issues, a dynamic soft reset mechanism is implemented, automatically reinitializing the seed whenever a repeating pattern is detected. So this ensures a community of unpredictable sequence without manual interventions. So this PRNG designs are implemented and tested on FPGA platforms with a performance metrics including the repetitions, durations, power consumptions and resource utilizations analysis for each polynomial configurations. The experimental results demonstrate the effectiveness of the proposed approach, particularly highlighting how the 32-bit polynomial configurations extends the durations before repetitions while maintaining the efficient resource usage. So this work provides a significant contribution to the field of FPGA hardware-based PRNG, offering optimized solutions for applications requiring high level of randomness and security. So now we can verify the paper. So this paper is fully designed for the pseudo random number generator. So here they are use two different architectures. The first one is a basic structure of the 8-bit LFSR. So the PRNG means it's always developed using LFSR technique. So LFSR means a linear feedback shift registers. So it will be designed using number of D flip-flops. Okay, so here the number of outputs from the intermediate of D flip-flop will be exerted and it will be given to the feedback. That is a polynomial equations. Okay, so here the polynomial 1 and polynomial 2 they are given x power 8, x power 6 and x power 5 and x power 4 plus 1. Okay, which means the x power 8 means the 8th D flip-flop and 6th D flip-flop and 5th D flip-flop and 4th D flip-flop plus the 1, the first D flip-flop. Okay, so it will be exerted and it will be given, the output will be given to the feedback of the final D flip-flop. That is a polynomial method. Okay, so here as per the polynomial method, here they are designed two different architectures. One is for figure 2 and one is for figure 3. Okay, the second one, and the figure 2 considers the two design seed with identical polynomial. Okay, so here you can analyze it. So the both LFSR techniques is almost same. Okay, but they are given different number of seeds. Okay, and based upon different seeds it will be generating a different pattern. Okay, so based upon that pattern it will be generating the output with support of this XOR gate. Okay, but this figure 3 is another proposed one. This is a two dozen polynomial and one seed. Okay, so here one seed only they are given, but here they are generated a two different polynomial technique. Okay, so the first polynomial differ with the second polynomial. Okay, so as per that it will be generating the output in the support of XOR gate. Okay, so here what is the advantages means here we need to give two seed. Okay, but here we are given only one seed of the operations. Okay, internally we will be change the polynomial code. Okay, so here it will be take more advantages. Why? Because here IOB will be take very less. Okay, so in the same cases this 8-bit seeds and 8-bit LFSR technique, so some of the time it will be take repeated patterns it will be generated. Okay, so we need to plan to avoid this repeating pattern. That's why we create this proposed architectures to reinitialize the seed value. Okay, so that's why we are given a dynamic seed value. So that seed value will reset whenever the data will be repeating. Okay, at the time it will be a newly created seed they are using to generate patterns again continuous. Okay, so as per that we have created a Verlagestel code here for 8-bit polynomial and 16-bit polynomial and 32-bit polynomial. Okay, and this code also we have simulated in ModelSims. Okay, this is a ModelSim software simulation pattern. This is a 8-bit polynomial PRNG output. Okay, so here this is a random number generator. Okay, so here this is a PRNG output, so it's given in a unsigned or decimal values. Okay, and the waveforms also given, okay, as per the random pattern. Okay, so random pattern we can analyze it in the waveform. Okay, it will be easy to analyze so the repeated patterns will be generated or not. Okay, so if the repeated pattern generated, okay, so the dynamic enable and dynamic seed will be initialized here. Okay, so here we are analyzing the repeated pattern with support of some registers. Okay, so here you can analyze it. Okay, so register x1 and px1. Okay, so here we are comparing the data. So this data, it will be same. Okay, same means it will be generating the result. Okay, so here I can analyze it, the 169 and 169, 82 and 82, 165 and 165. It will be repeating. Okay, so at the time the dynamic enable will be generated, and the dynamic seed reinitialize the polynomial sequence, polynomial 1 and polynomial 2. Okay, and then it will be start generating the pattern continuously. Okay, with a new pattern format it will be generated. Okay, here, so it's mostly used for the cryptography applications to create a long term of encryptions. Okay, so here in the same way for 16-bit. Okay, so this is a 16-bit code, 16-bit pattern generations. Okay, and this is for 32-bit pattern generations. Okay, so here compared to this 8 and 16, the 16-bit code will take up to the 800 microsecond we are executed, so it will be take the 4 times only occupied. Okay, with the dynamic resets. Okay, but in the 32 code it will be take more long time, because we need to calculate up to the 2 power 32. Okay, so based upon the cycles it will be not generated up to the 800 microseconds, so we need to run more long time. Okay, then only we can get a repeating data pattern. Okay, in the 32-bit, so it's compared to 8-bit and 16-bit, the 32-bit was more accurate here. Okay, so here this works, we have synthesized in Xilinx Vertex 5 FPGA. So here this is a synthesized results for 8-bit. Okay, so here you can check the RTL schematic. Okay, so this is a polynomial 1 and polynomial 2 code, and this is a XOR gate. Okay, and this is a dynamic seed generations. Okay, so here the dynamic seed generations comparing the bits of PRNG output. Okay, so PRNG output, you are get a feedback to the dynamic seed generations. As per the feedback, it will be comparing the data with some registers. Okay, at the time it will be taking the decisions from the PRNG output. Okay, so this is a polynomial code. Okay, so completely XOR operations we are doing here. Okay, and this is a XOR gate. Okay, so here this is a logic synthesize. Okay, and this is a 16-bit, and this is for 32-bit. Okay, so this comparisons parameters we have built in the comparisons table. So here this is a comparisons. Okay, and we have developed a proposed abstract document here. Okay, so here you can analyze a base paper abstract, improvement of the projects, proposed title, proposed abstract, existing systems. Okay, so disadvantages, okay, advantages and related notes for this project. Okay, and literature survey, finally references. Okay, so additionally we are given a reference paper for this book. Okay, thank you.